Earth rarely captures the world's attention all at once, but over the course of just a few days, powerful earthquakes struck in different corners of the globe, from South America to East Asia and beyond. News headlines quickly filled with reports of damaged cities, tsunami alerts, and scientists monitoring active fault lines. To many people, it seemed as if the entire planet had suddenly become more unstable. Whenever several major earthquakes happen close together, one question almost always follows. Are these disasters somehow connected, or is the Earth entering a period of unusual seismic activity? It is an understandable reaction. Seeing multiple powerful earthquakes appear in rapid succession naturally creates the impression that something larger may be unfolding beneath our feet. But appearances can be misleading. In this video, we're going beyond dramatic headlines to examine what modern geology actually tells us. We'll look at the science behind these recent earthquakes, explore why some regions suffer catastrophic losses while others recover with surprisingly little damage, and examine new research that has renewed attention on some of the world's most closely watched fault systems. The goal isn't to predict the next disaster or fuel unnecessary fear. It's to understand how our planet works, what experts have learned, and why preparation often matters just as much as the earthquake itself. Venezuela's devastating double shock, the most devastating example of this recent wave of seismic activity unfolded in Venezuela, where a powerful sequence of earthquakes transformed ordinary life into a humanitarian emergency in less than a minute. Unlike a single earthquake followed by smaller aftershocks, this event involved two major ruptures occurring only seconds apart, leaving little time for people to react before the strongest shaking arrived. One of the most important factors behind the destruction was the earthquake's shallow depth. When seismic energy is released close to the Earth's surface, far less of that force is absorbed by surrounding rock. Instead, much of the energy reaches buildings directly, producing far more intense ground motion than an earthquake of similar magnitude, occurring much deeper underground. But geology alone does not determine the scale of a disaster. The condition of the built environment plays an equally critical role. Many neighborhoods in the affected region contained older buildings that were never designed to withstand strong seismic forces. Structures built without modern earthquake-resistant engineering are especially vulnerable because they lack the flexibility needed to absorb sudden horizontal movement. As the ground shifted violently, many buildings simply could not withstand the stress. The impact quickly spread beyond collapsed structures. Electricity failed across large areas, communication networks became overloaded, and transportation routes were disrupted just as emergency responders needed them most. Hospitals faced an immediate surge of injured residents, while rescue teams raced to reach communities where damaged roads and fallen debris slowed every operation. For thousands of families, the uncertainty became just as painful as the earthquake itself. Loved ones struggled to contact one another, while search and rescue crews worked around the clock to locate people trapped beneath damaged buildings. As international aid organizations began arriving, the enormous challenge became clear. Recovering from a disaster is far more difficult when critical infrastructure has already been under pressure for years. The Venezuela earthquake serves as a powerful reminder that the true impact of a seismic event is measured by more than its magnitude. Factors such as construction quality, emergency planning, healthcare capacity, and infrastructure resilience often determine whether an earthquake becomes a difficult emergency or a national catastrophe. In the end, the movement of tectonic plates cannot be controlled, but the strength of the communities built above them can make all the difference. Why similar earthquakes produce different outcomes? At nearly the same time that Venezuela was struggling with widespread destruction, another powerful earthquake struck Japan. On paper, the two events appeared remarkably similar. Both were strong enough to trigger international attention, widespread shaking, and emergency warnings. Yet the final outcomes could not have been more different. The difference was not simply a matter of luck. It was the result of decades of preparation. Japan is one of the most seismically active countries on Earth, sitting where several tectonic plates interact. Because earthquakes are an unavoidable part of daily life, the country has spent generations investing in ways to reduce their impact. Modern building codes require structures to absorb and dissipate seismic energy rather than resist it rigidly. Many high-rise buildings are designed to sway safely during intense shaking, while critical facilities, such as hospitals, bridges, and transportation networks, are built with additional layers of protection. Preparation extends far beyond engineering. Earthquake response is woven into everyday life. Schools regularly conduct evacuation drills, businesses practice emergency procedures, and public agencies maintain clear communication systems that activate within seconds of a major event. When tsunami warnings are issued, residents understand where to go and how to respond without waiting for further instructions. Technology also plays a major role. Japan operates one of the world's most advanced earthquake early warning systems, capable of detecting the first seismic waves and sending alerts before the strongest shaking arrives, although the warning may provide only a few seconds. That brief window allows trains to slow automatically, factories to pause sensitive operations, surgeons to protect patients, and millions of people to take cover. The contrast between Japan and Venezuela demonstrates a crucial reality about earthquake disasters. While the force of nature cannot be controlled, the consequences often can be reduced. Similar magnitudes do not guarantee similar levels of destruction because the final outcome depends on far more than the earthquake itself. Experts often emphasize that earthquakes do not kill people. Unsafe buildings, inadequate infrastructure, and limited preparedness do. Japan's experience shows what long-term planning can achieve. By combining scientific research, strict engineering standards, public education, and continuous investment in resilience, the country has transformed many potentially catastrophic earthquakes into emergencies that can be managed far more effectively. This comparison offers an important lesson for every nation located near active fault lines. The time to prepare is not after the ground begins to shake. The decisions made years before an earthquake occurs often determine how many lives will be protected when that moment finally arrives. Southern California's growing seismic concern. While Venezuela highlights the devastating consequences of a major earthquake and Japan demonstrates the value of long-term preparedness, scientists are paying close attention to another region where the next significant event could have global attention: Southern California. At the center of that concern is the San Andreas Fault, one of the most studied fault systems on the planet. Stretching hundreds of miles across California, it marks the boundary where the Pacific Plate and the North American Plate slowly slide past one another. This movement happens continuously, but not always smoothly. In many places, friction locks the fault in position while the tectonic plates continue pushing against each other, allowing stress to build over time. Recent scientific research has suggested that portions of Southern California's fault network have accumulated exceptionally high levels of strain. That does not mean an earthquake is about to happen tomorrow, next month, or even next year. Earthquake science has not reached the point where researchers can predict the exact timing of a major rupture. What these studies do indicate is that the conditions necessary for a powerful earthquake continue to develop as stress gradually increases beneath the surface. Another reason researchers are watching the region so carefully is that the San Andreas Fault does not exist in isolation. It is part of a complex network of interconnected faults spread throughout Southern California. Some geological models suggest that under certain circumstances, movement on one fault could influence neighboring fault systems, creating a larger rupture than would occur on a single fault alone. Although this remains an area of active research, emergency planners increasingly consider these multi-fault scenarios when preparing for future disasters. The stakes are enormous because Southern California is home to millions of people and some of the most important infrastructure in the United States. Major highways, airports, rail networks, hospitals, water systems, power grids, and communication lines all serve one of the world's largest metropolitan regions. Even if modern buildings perform well, widespread disruptions to transportation and essential services could affect daily life for weeks or even months. California has made significant progress in earthquake preparedness over the past several decades. Building codes have become much stricter. Many older structures have been retrofitted, and statewide early warning technology continues to improve. Yet experts agree that preparedness remains an ongoing process. Thousands of older buildings still require upgrades, and emergency agencies continue encouraging residents to create disaster plans before the next major earthquake occurs. The key message from scientists is measured rather than alarming. They are not predicting a specific date or claiming disaster is inevitable in the immediate future. Instead, they are reminding us that earthquakes are part of California's natural geology, and preparation should evolve alongside the latest scientific understanding. The goal is not to create fear, but to reduce future risk by acting before the ground begins to move. Are these earthquakes actually connected? Whenever several major earthquakes occur within a short period, it's natural for people to wonder whether they are part of a larger global pattern. Social media often fills with claims that one earthquake triggered another thousands of miles away, or that the planet is entering an unusually active phase. It's an understandable question, but the scientific answer is more complex. In most cases, large earthquakes occurring in different parts of the world are not directly connected. Each earthquake is usually the result of stress building over many decades, or even centuries, along its own fault system. When that accumulated pressure finally exceeds the strength of the surrounding rock, the fault suddenly slips, releasing energy in the form of seismic waves. This process happens independently across different tectonic plate boundaries. To understand why, it helps to look at how Earth's outer shell is organized. The planet's surface is divided into massive tectonic plates that move slowly over the semi-fluid mantle beneath them. These plates collide, separate, or slide past one another at different locations around the globe. Because each boundary has its own geological history and stress conditions, an earthquake in one region rarely causes another on a completely separate plate thousands of miles away. Many of the recent earthquakes occurred around an area known as the Pacific Ring of Fire, a vast horseshoe-shaped zone that surrounds much of the Pacific Ocean. This region contains numerous active plate boundaries and is responsible for the overwhelming majority of the world's strongest earthquakes and volcanic eruptions. With so many active fault systems concentrated in one area, it is statistically normal for multiple significant earthquakes to occur there within the same week or month. What has changed over time is not the Earth's behavior, it is our own. Today's world has far larger cities, denser populations, and more critical infrastructure built near active fault lines than ever before. As urban areas continue to expand into seismically active regions, the human impact of earthquakes becomes increasingly significant. So while recent events may appear connected when viewed through the headlines, geology tells a different story. These earthquakes are not signs that the planet has suddenly become unstable. Instead, they remind us that Earth has always been dynamic. The real challenge lies not in changing the planet's natural processes, but in ensuring that the communities living above those fault lines are prepared for the inevitable movement beneath them. Understanding magnitude beyond the numbers. When an earthquake is reported, the first number most people notice is its magnitude. A 6.5, a 7.2, or an 8.0 instantly becomes the headline, but that single number only tells part of the story. To understand how destructive an earthquake can be, it's important to know what the measurement actually represents. Earthquake magnitude is measured using a logarithmic scale, which means each increase represents a dramatic jump in released energy rather than a small step upward. A magnitude 7 earthquake is not just slightly stronger than a magnitude 6. It releases many times more energy. As magnitudes continue to rise, the increase becomes even more significant, which is why scientists pay such close attention to earthquakes above magnitude 7. However, magnitude alone does not determine how much damage an earthquake will cause. Depth is one of the most important factors. An earthquake occurring deep beneath the Earth's surface allows much of its energy to weaken before reaching populated areas. In contrast, a shallow earthquake delivers far more of its force directly to the surface, producing stronger shaking, even if its magnitude is similar to a deeper event. Location is equally important. A powerful earthquake beneath an uninhabited region may cause little more than scientific interest, while a smaller event directly beneath a densely populated city can become a major disaster. The distance between the fault and nearby communities often determines how intensely people experience the shaking. Local geology also plays a surprisingly large role. Soft soils, river sediments, and a reclaimed land can amplify seismic waves, making buildings shake far more violently than those constructed on solid bedrock only a few miles away. This explains why damage often varies dramatically across different neighborhoods during the same earthquake. Finally, the quality of construction can be the deciding factor. Modern buildings designed under strict seismic standards are engineered to absorb movement and remain standing even during strong earthquakes. Older structures built before those standards existed are generally much more vulnerable to collapse. For scientists, evaluating an earthquake means examining all of these elements together: magnitude, depth, location, local ground conditions, and engineering quality combine to determine the real-world impact. That's why two earthquakes with nearly identical magnitudes can produce completely different outcomes, reminding us that understanding seismic risk requires looking far beyond a single number. Cities. Scientists continue to watch closely. Although California often dominates discussions about earthquake risk in the United States, it is far from the only region that keeps seismologists alert. Around the world, several major cities sit beside active fault systems, where decades or even centuries of accumulated stress continue to build beneath millions of residents. One of the most closely monitored cities is Istanbul, Turkey. Home to more than 16 million people, the city lies near the North Anatolian Fault, one of the most active strike-slip fault systems on Earth. Over the past century, this fault has produced a sequence of powerful earthquakes that have gradually migrated westward. Because of this pattern, many researchers believe the section beneath the Sea of Marmara remains one of the most significant seismic risks in the region. Like many rapidly growing metropolitan areas, Istanbul faces a difficult challenge. While thousands of newer buildings have been constructed using stronger engineering standards, many older structures were built before modern seismic regulations existed. Retrofitting an entire city is a massive undertaking that requires years of investment, careful planning, and consistent enforcement of building codes. Other major cities share similar concerns. Manila, Mexico City, Santiago, Lima, and parts of New Zealand all exist in regions where tectonic activity is a normal part of Earth's geology. Each city faces different hazards depending on its location, but they all share one common reality. Earthquakes are not rare possibilities. They are expected natural events over long enough timescales. Scientists emphasize that population growth has become one of the biggest factors influencing earthquake risk. As cities expand, more homes, hospitals, schools, highways, and communication systems are built in areas vulnerable to strong ground shaking. This means that even if the frequency of earthquakes remains relatively stable, The number of people and critical services exposed to potential damage continues to increase. For emergency planners, the goal is not to identify which city will experience the next major earthquake first. Instead, the focus is on strengthening infrastructure, improving emergency response systems, and encouraging communities to prepare well before disaster strikes. The lesson, repeated across every high-risk region, is remarkably consistent. While no city can eliminate earthquake risk, every city has the opportunity to reduce its consequences through thoughtful planning and long-term resilience. Technology that buys precious seconds. For decades, one of the biggest challenges in earthquake science has been prediction. Despite enormous advances in geology, researchers still cannot determine the exact day, hour, or location where a major earthquake will occur. Instead of trying to forecast the impossible, scientists have focused on a different goal, giving people as much warning as physics allows. That effort has led to the development of earthquake early warning systems, one of the most important advances in modern disaster preparedness. The technology works because earthquakes generate different types of seismic waves. The first waves, known as primary waves or P waves, travel at the highest speed but usually cause only light shaking. They are followed by secondary waves, or S waves, which move more slowly but carry the powerful ground motion responsible for most structural damage and injuries. By detecting the fast-moving P waves, networks of highly sensitive seismic sensors can instantly calculate the location and estimated strength of an earthquake. Automated systems then transmit alerts before the slower, more destructive S waves arrive. Depending on how far someone is from the epicenter, that warning may last only a few seconds, or in some cases, several tens of seconds. At first glance, that may not seem like much time. In reality, those few seconds can make a remarkable difference. An early warning allows people to move away from windows, take cover beneath sturdy furniture, or step clear of objects that could fall during intense shaking. Hospitals can pause delicate procedures, elevators can stop at the nearest floor and open their doors, and high-speed trains can begin emergency braking before reaching bridges or tunnels. Industrial facilities can automatically shut down sensitive equipment, reducing the risk of secondary accidents after the earthquake begins. Countries such as Japan have demonstrated how effective these systems can become when combined with public education. Millions of residents receive alerts directly on their mobile phones and understand exactly how to respond, because earthquake drills are part of everyday life. California has also expanded its statewide warning network, integrating alerts into public safety systems and smartphone applications while continuing to improve detection speed and coverage. However, technology alone is not enough. An alert only saves lives if people know what to do when they receive it. The combination of reliable warning systems, regular emergency drills, strong engineering standards, and public awareness creates multiple layers of protection that work together during those critical first moments. Earthquakes cannot be stopped, but preparation can begin before the strongest shaking arrives. Sometimes, just a few seconds of advance notice are enough to turn panic into action, and action can save lives. The real lesson behind every earthquake. When we look back at the earthquakes we've explored, one conclusion becomes impossible to ignore. The Earth itself is behaving exactly as it has for billions of years. Tectonic plates continue to move, stress continues to accumulate beneath the surface, and from time to time, that energy is released in the form of powerful earthquakes. These natural processes are not new, and they are not something humanity can prevent. What we can influence is what happens when the shaking begins. The contrast between different countries demonstrates that earthquake disasters are shaped by far more than geology alone. Strong building standards, reliable emergency communication, resilient infrastructure, and a well-prepared public can dramatically reduce the human cost of even the most powerful earthquakes. Communities that invest in preparedness before disaster strikes are often able to recover faster and protect far more lives. That is why experts consistently encourage households to take simple but meaningful steps long before an emergency occurs. Keeping basic supplies such as drinking water, non-perishable food, flashlights, batteries, first aid materials, and essential medications can make the first few days after a major earthquake much safer. Every family should also have a communication plan, know safe places inside their home, and understand local evacuation procedures if they live in a high-risk region. These preparations may seem ordinary today, but they become invaluable when normal services are disrupted. Earthquakes often damage roads, interrupt electricity, and overload communication networks, making self-sufficiency during the first hours especially important. The recent earthquakes around the world remind us of an important truth. Nature will continue to reshape our planet, regardless of where we live or how advanced our technology becomes. But every new scientific discovery, every improvement in engineering, and every lesson learned from past disasters gives us another opportunity to become more resilient. Here at Nebulix, our goal is not to create fear. It is to understand the science behind the headlines and explore how knowledge can help societies prepare for the future. As researchers continue monitoring active fault systems and improving our understanding of Earth's dynamic geology, We'll continue bringing you clear, fact-based analysis of the discoveries that matter most. Have you ever experienced an earthquake yourself? What did it feel like, and how did your community respond? Share your experience in the comments below. Your story could help others better understand what these events are truly like beyond the statistics. And if you enjoy in-depth documentaries exploring space, science, and the powerful forces that shape our world, be sure to subscribe to Nebulix so you don't miss our next exploration.